13th International Physics Olympiad, year 1982, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F1996. Problem number 1. Fluorescent lamp. An alternating voltage of 50 Hz frequency is applied to the fluorescent lamp shown in the accompanying circuit diagram. The following quantities are measured. Overall voltage, main voltage, U equal 228.5 volt. Electric current, I equal 0.6 ampere. Partial voltage across the fluorescent lamp, U prime equal 84 volt. Ohmic resistance of the series reactor, RD equal 26.3 ohm. The fluorescent lamp itself may be considered as an ohmic resistor in the calculations. Question A. What is the inductance L of the series reactor? Question B. What is the phase shift phi between voltage and current? Question C. What is the active power PW transformed by the apparatus? Question D. Apart from limiting the current, the series reactor has another important function. Name and explain this function. Hint. The starter S includes a contact which closes shortly after switching on the lamp, opens up again and stays open. Question E. In the diagram with the quantitative time scale, sketch the time sequence of the luminous lux emitted by the lamp. Question F. Why has the lamp to be ignited only once? Also, the applied alternating voltage goes through zero in regular intervals. Question G. According to the statement of the manufacturer, for a fluorescent lamp of the described type, a capacitor of about 4.7 microfarad can be switched in a series with the series reactor. How does this affect the operation of the lamp, and to what intent is this possibility provided for? Question H. Examine both halves of the displayed demonstrator lamp with the added spectroscope. Explain the differences between the two spectra. You may walk up to the lamp and you may keep the spectroscope as a souvenir. Solution for problem number 1. Question A. What is the inductance L of the series reactor? The total resistance of the apparatus is Z equal U over I, which is 380.8 ohm. The ohmic resistance of the tube is RR equal U prime over I, which is 140 ohm. Hence, the total ohmic resistance is RR plus RD, which is 166.3 ohm. Therefore, the inductance of the series reactor is omega L equals square root from Z square minus R square, which is 342.6 ohm. This yields that inductance L equal omega L over 2 pi F, which is 1.09 Henry. That was solution for question A. Question B. What is the phase shift phi between voltage and the current? Solution. The impedance angle is obtained from tangent phi equal omega L over R, which is 2.06. It means that phi equals 64.1 degrees. That was solution for question B. Question C. What is the active power TW transformed by the apparatus? Solution. The active power can be calculated in different ways. First way, that's equal to U multiplied by I and multiplied by cosine phi, which is 59.88 watt. Another way is equal to R multiplied by I square, which is 59.87 watt. That was solution for question C. Question D. Apart from limiting the current, the series reactor has another important function. Name and explain this function. Hint. The starter S includes a contact which closes shortly after switching on the lamp, opens up again and stays open. Solution. By opening the contact in the starter, a high induction voltage is produced across the series reactor, provided the contact does not open exactly the same moment when the current goes through zero. This voltage is sufficient to ignite the lamp. The main voltage itself, however, is smaller than the ignition voltage of the fluorescent tube. That was solution for question D. Question E. In a diagram with a quantitative time scale, sketch the time sequence of the luminous flux emitted by the lamp. Solution. This is the diagram where 20 milliseconds correspond to frequency 50 Hz. So that was a solution for question E. Question F. Why has the lamp to be ignited only once, although the applied alternating voltage goes through zero in regular intervals? Solution. The recombination time of the ions and the electrons in the gaseous discharge is sufficiently large. That was solution for question F. Question G. According to the statement of the manufacturer, for a fluorescent lamp of the described type, a capacitor of about 4.7 microfarad can be switched in series with the series reactor. How does this affect the operation of the lamp, and to what intent is this possibility provided for? Solution. Resistance of the capacitor of 4.7 microfarad is 1 over omega C, which is 677.3 ohm. The two reactances subtract, and the remaining resistance of 334.7 ohm acting as a capacitor. The total resistance of the arrangement is now Z prime equal 373.7 ohm, which is very close to the total resistance without capacitor, if you assume the capacitor to be loss-free as in question A. Thus, the lamp has the same operating qualities, igniting the same way, and the difference is found only in the impedance angle phi prime, which is opposite to the angle phi calculated in B. Now we have tangent phi prime equal negative 2.01 and the phi prime equal about negative 63.6 degrees. Such additional capacitors are used for compensation of reactive currents in buildings with a high number of fluorescent lamps. Frequently they are prescribed by the electrical supply companies. That is, a high portion of reactive current is unwelcome, because the power generators have to be laid out much bigger than would be really necessary, and the transport losses also have to be added, which are not paid for by the customer if pure active current meters are used. So that was solution for question G. Question H. Examine both halves of the displayed demonstrator lamp with the added spectroscope. Explain the differences between the two spectra. You may walk up to the lamp and you may keep the spectroscope as a souvenir. Solution. The uncoated part of the demonstrator lamp reveals the line spectrum of mercury. The coated part shows the same line spectrum of a continuous background. The continuous spectrum results from the ultraviolet part of the mercury light, which is absorbed by the fluorescent and re-emitted with a smaller frequency, energy loss of the photons or larger wavelength respectively. That was solution for question H, and here we finished discussion for problem number 1.